Also, welcome to our webinar. Today we will learn more about perovskite-silicon tandem solar cells. We will have two speakers. There is Dr. Erkan Aydin from LMU and Dr. Urs Eberhard from Fluxin. The first talk focuses more on fabrication, characterization of tandem PVs, whereas the second is on the simulation optimization. Erkan is a pleasure to have him here. He's a well-known researcher working on perovskite solar cell from KAUST. Recently, he started as a group leader at LMU in Munich. He has a PhD from top university in Turkey, and as I said, he went at KAUST, where he achieved record efficiency in perovskite-silicon tandem solar cells. He now directs the Space project. This is an ERC starting grant. He's going to develop space-grade perovskite-based tandem solar cells.
Well, today, as you mentioned, actually, I will try to talk about the recent progress that we have made at KAUST for the perovskite-silicon tandem cells. Well, why I have a problem? All right, okay. Before starting, first of all, and I have to tell you that this majority of the works that I have done here, I will present here, have been house and 2016 and 2023, 2024, last 7.5 years, I worked with several researchers at KAUST and also collaborated with several well-known institutes. And today, actually, as I said, I will talk about the research basically made by the team and myself at KAUST KPV Lab. Here, I mean, especially for in 2021 and 2022, you see that the total installed capacity per year is majorly composed of by the solar photovoltaics. And I don't have the numbers for 2023, but there is actually solar photovoltaics more and more. And recently, actually last year, we already exceeded the 1 terawatt installed capacity. This number was already 500 gigawatt in 2018. And in a few years, this number jumped to 1 terawatt level. And actually, from now on, we are talking about terawatt scale power generation technology. It's a huge capacity. Actually, this is exponentially increasing. In 2023, our total installed capacity, increased well beyond the 1 terawatt with added capacity of 350 gigawatt in 2023. And this number will be reaching maybe the 500 gigawatt and beyond in 2024. Obviously, if in 2018, 6 years ago, the total capacity was 500 gigawatt, but still recently we are expanding the capacity more and more. Well, it's a good news again, because all the countries made an agreement with the Paris Agreement. We want to do transition to clean energy as soon as possible. And there is a goal to complete this transition by 2050 for many countries. They put a signature on this. There is a recent policy article came out in Science. And in this policy article, and the Nancy Hegel and also the large team, they explain what should be our goal for the next years. Basically, we are expecting a 25% market growth by 2033, sorry. And actually, we have to increase the manufacturing capacity until 3 terawatt per year. This is not installed capacity, it's a manufacturing capacity. And if we do that, and actually in 2050, we can reach the capacity of 70 terawatt. And actually, this is a predicted realistic scenario for utilizing the solar photovoltaics. So you can understand that from the level of the 2 terawatts to 70 terawatt, we need a lot of solar cells to be installed and to be manufactured. For sure, if if you want that more solar panels are deployed, then we have to make it more competitive. Um, good thing is that solar photovoltaic panels, they are really already competitive as of 2023 among the all other renewables, and also for sure fossil fuels compared to them. Photovoltaics are really cost effective. And actually, recently there is a record low the module prices, PV module prices, as you know, for the PERC modules recently, and this decreased the 10 cent per watt level. And actually, the further reductions are really possible. I mean, basically, the whole community is working for this. But in the long run, the PV cost is driven by the performance of the PV systems, because the PV module prices, there are some other costs, we call them balance of system costs, including there are some thermodynamic losses, Carnot loss, and there is a Boltzmann loss, and these are the losses we hardly recover, because these are actually basically the entropy losses, and also the Boltzmann losses are mostly related to emission angle of the black body radiation. So basically, but there is a huge contribution to the losses from most of the thermalization losses, as you see here. So this is the power output from the from the semiconductors that we can get out. But actually, we lost a lot of things with the thermalization. Tandem cells are good then, because we can minimize this thermalization losses by utilizing the spectrum more effectively. But for sure, for this we have to use I mean, we have to couple the good semiconductor with another good semiconductor. And this is a very popular graph, frequently updated by Amol. Ideally, if you make a tandem cell, you need to choose a semiconductor within this blue band. This is the 75% of the details balance limit. So basically, and we have some few options: gallium arsenide, gallium indium phosphate. They are already well-known tandem technologies. Here, the perovskite is quite promising. I think majority of the audience of this talk knows why the perovskites are really high quality semiconductors. And as I said, we have to use the speckle more effectively. And if you use only the crystalline silicon, we are able to utilize this portion of the solar spectrum. The orange line, the shaded area, is the solar spectrum intensity. And if you put any, so we have to make them also cost effective, and we have to be able to fabricate them with a scalable method. And this should be a reliable technology if you want to reach such a high level. So for these perovskites and silicon, they are a good couple, definitely. We can tune the band gap of the perovskite to maximize the light coupling. And also we can do them in the multiple configurations. Basically, here you see we can fabricate 2-terminal, 3-terminal, or 4-terminal tandem cells, and they can be in the monolithic form, they can be in the mechanical stacking form, and we have a lot of module configurations. But I will reiterate the expression again. I mean, so far we don't have any gigawatt scale tandem technology so far that we utilize, and most of the tandem technologies basically used for concentrated photovoltaics or space photovoltaics, and the cost was not a primary factor over there. But here we have to make them really large area and large volume manufacturing. Well, and how this perovskite silicon tandem solar cells looks like, and basically we have a quite a thick silicon wafer, and I'm saying thick because compared to the perovskite, it's pretty much thick. Today, the industrial wafers usually their thickness is around 150 and 180 micrometers, and for the academic works, people mostly use the 250 microns. And well, the total thickness of the perovskite layer is basically less than 2 micron. And imagine that we are just depositing a kind of nano layers on top of the crystalline silicon wafers, and we are forming the tandem cell. Here, crystalline silicon cells are absorbing the near-infrared light, as you see here, and also the perovskite portion is mostly absorbing the blue spectrum, as I also showed on the solar spectrum a few slides before. All right. Well, actually, I'll talk about a little bit what kind of progress we have made so far on the optical design of these devices, because the light coupling is quite important to make efficient tandem cells. And for sure, I mean, the light coupling is highly dictated by also the bottom cell choice, and there are three mainstream crystalline silicon technologies at the moment in the market, and the most dominant one is the PERC. And the PERC, as you see, that the typical process involves the front contact is textured, rear side is planar, and usually there is I mean the nitride layer, insulating layer, and there is the silver contacts diffuse through by the local openings, and they also diffuse through these the front contacts. Well, I mean the PERC cells are a bit tricky to make a tandem cell because usually we don't have a direct access to recombination junction here. In TOPCon, this is a bit more flexible that we can do indeed high temperature processing cells, and the rear side is pretty similar to PERC, but in the front side we can also accommodate indium tin oxide or any other kind of TCO. If we remove this, how to say, the nitride layer, it is possible to make the recombination junction on the TOPCon cells. But on the other hand, if you look at the right-hand side, silicon heterojunction is also quite promising, and then we can do double-side texturing with this configuration. Basically, we have a symmetrical passive waiting contacts in the front side. We have directly transparent conductive oxide. We don't need to fire through these front electrodes, so we can use also the front TCO directly as a recombination layer. That's why recently majority of the works in the perovskite-silicon tandem field is coming from the silicon heterojunction, so basically we are getting a better spectral response, minimize the reflections, and also easy to fabricate. And texturing is important and is not something new. If you look at this graph, actually it's explaining nicely. It's from an article from 1987. So basically it's not something new. Well, actually the silicon is basically, it's an indirect bandgap semiconductor. Its absorption coefficient is pretty low, and compared to direct semiconductors for sure. And in this case, we need to help silicon to absorb the light more, and we want that the light is bouncing more inside the silicon. So that's why we put a texturing in the front and rear side. Basically, this is not a very complicated thing, but it's a very smart way to do that. We just slice the wafers by aiming that the planar side is 100 plane, because these are single crystal. And when we etch away, then we form this kind of pyramidal shapes in the front surface. And by tuning the size and the distribution, we can really minimize the reflection on the silicon cells. And as you see here, if we make a double-side texturing, we can really approach to the Lambertian limits, and that's very good. And this is also standard thing in the industry, but the problem is now here. If you want to fabricate the perovskite on such layers, the problem is that you have to make good coverage on these pyramids. You shouldn't have any open the pyramids because basically they will be touching your front TCO and it will be causing a shunt. So vacuum techniques are pretty good for this, but actually so far the vacuum-based techniques are not as efficient as the solution-based techniques. But so solution-based techniques, spin coating, slow die coating, we have to really levelize the perovskite to make sure that none of these pyramids are coming out. And this was also the case when we tried, when we attempted first time to spin coat the perovskite on top of the commercial grade crystalline silicon wafers, and the very first thing that we found was the pyramids were actually coming out, and basically this device is by default shunted. So we overcame this issue by following a few steps strategy. First, actually, we studied to reduce the pyramid size, and because typically the pyramid size in the market was around, around the 5 micron, 6 micron level. And the idea was reducing the pyramid size, still enabling a continuous distribution, homogeneous distribution on the crystalline silicon surface, and still we minimize the reflection with a meaningful pyramid size. And for this, we did several optimizations by the etching process, and we found that actually the 2 micrometer and less is the ideal thickness, is for the perovskite-silicon tandem cells. If you use a spin coating method, the next challenge was making it a bit thick. So basically, we use a bit more concentrated precursor solutions and optimize the process further. And indeed, actually, this strategy worked. As you see on the right-hand side, we really minimize the reflections, especially for in the near-infrared region. So basically, this strategy worked well, and we minimize the reflections on the pyramidally textured bottom cells. Well, I mean, for sure, if you deposit the conformal layer, you can get the similar effect, even better. But our method enabled to make a solution process perovskites on textured interfaces. So after that, yeah, I mean, okay, we have a good perovskite, but we also did some optimization on the contacts, because for we have a lot of losses because we have a lot of layers are stacked in the tandem cell. Usually more than 15 layers are stacked. And in this case, the smart thing is that playing with the optics and minimizing the parasitic losses. And for this, we used a different strategy than the literature. Actually, this is not something new. Again, it's a well-known thing in the literature, but we just adopted it for our tandem cells in a proper way. And basically, for these devices, you have to displace the rear contact, the metal contact, to get to approach the ideal mirror conditions. You don't want too much plasmonic absorptions at the metal semiconductor interface. And but for sure, the typical thing have been used so far was a thick TCO, and usually the thickness around 120 nanometers, and the TCO is basically absorbing light a lot. In this case, what we did, we thinned down the TCO at the rear side, and we put a low refractive index material, magnesium fluoride. You can also put something else between the silver and the ISO contacts, and we actually approach the ideal mirror condition. By doing this, actually, we enhance the current density a lot, because we minimize the parasitic absorption losses at the rear contact of the tandem cells. We did a similar strategy at the front side, because the light is coming from the front side. Definitely, any parasitic losses will cost us the current losses. So basically, here, one of the biggest contribution was coming from the front TCO, and we did the thickness optimization by doing a power loss analysis. And then actually we found that if you use a 40 nanometers, we are matching the current density, the subcells nicely, and also we minimize the absorption losses, especially for in the deep blue part. Well, the other contribution is also for sure, from the front contacts, because if you use a resistive TCO, then you have to put more fingers for efficient charge collection. In this case, and we had to optimize also the number of the fingers and their distribution. And in this case, we maximized also the power conversion efficiency by just tuning the fingers. And overall, a quick summary here. And what we get out from these optimizations, Well, if you look at this graph here, and especially for the rear ISO side, we had a huge reduction from the current losses, and also the front TCO that we had a huge reduction, and even at the recombination junction, we had a huge reduction. I'll come that point because in this work we also thin down the recombination junction further. And I'll speak a little bit about also more contact and interface engineering. The very first thing that we did some time ago, it was in 2022, again with my colleague Jian Liu, and actually we look the perovskite C60 interface, and because the overall idea was really minimizing the voltage losses as much as possible. So one thing that we did, um, we tried to figure out why there is a voltage losses even if you bring the energy level alignment of the perovskite and fullerene as close as possible. Uh, and actually, we were working with the calculation team, and then we understood actually if we approach to the fullerene layers towards the surface of the perovskite, we start to form a kind of defect states within the band cap, but not that this is not a defect state from the fullerene itself. These are actually induced defects, which means that it's like very well known thing in the silicon research as well is metal-induced gap states, and basically the wave functions of the perovskite and C60 are overlapping and it's behaving like a defect. So the only way to do that, displacing the contact between perovskite and fullerene, and this is done in the past by lithium fluoride, but this is not a viable option for the long term because lithium fluoride is a bit tricky. It's lithium is diffusing the perovskite and other contacts, and in the end, we lost this layer, and plus it's causing also performance losses. So uh, you can use any other metal oxide as well, not necessarily magnesium fluoride, but in this example, we found magnesium fluoride works very nicely. And actually, it is really displacing the contact, and we are not forming a continuous layer probably. Its ultra thin layer is around 1 nanometer, and then this is allowing the tunneling of the charge at the contact. So in doing so, we minimize the voltage losses and we increase the quasi-Fermi level splitting from the perovskite subcell. And overall, in this work at that time, we reached 29.3% efficiency. But for sure, we didn't stop there, and we continue looking for the other contacts, and this time the Hall selective contact. In 2020, when we introduced first time this double-side texture tandems with solution processing, we were using a nickel oxide. Then later on, we passivated nickel oxide because we found that there's a redox reactions are happening at the nickel oxide perovskite interface. But still we had the voltage losses, and then actually we also tried to adopt one of the best polymeric Hall transport layer in literature. It's a PTAA, and we tried to dope it, but we never reach a level that the conformal coverage with this method, although the sputtering was quite nicely. But later on in 2020, actually, the team of HZP and Kaunas, they introduced the surface and monolayers on tandem cells. Indeed, it was an interesting thing for us as well because we were able to form a conformal coverage on the textured interfaces. Basically, it's a self-limiting reaction, and in the end, what we get out from the cells, it was quite good. So, um, I mean, in this work, we focused on also the recombination junction. This is another important junction on another important layer in the perovskite-silicon tandem cells. So what we have done, and typically in the past we were using indium tin oxide at the recombination junction, but we understood actually the surface potential at the TCOs are different because especially for you see the extreme case here for indium zirconium oxide, and this is forming a large crystallite. Basically, these are polycrystalline materials, ITO and ISRO, And the polycrystalline materials, there are different grains and they have different grain orientations on the surface. And we understood that actually they already have a different potential distributions. And plus, if you anchor your SEMs on the surfaces, they also they also follow, mimic this trend. And in this case, our strategy was using actually the amorphous layer. And then we said, why we don't use indium zinc oxide because there is no crystal here. And we found that really the surface potential is start to be more homogeneous when we start using ISO, and even we after anchoring the self-SM monolayer on top of the ISO. So basically, at the recombination junction, we had a chance to minimize the inhomogeneities. And by doing so, we also achieved a better coverage of the SEMs, and this also reflected the work function shifts. And basically, this enabled us more homogeneous coverage of the SEMs on at the recombination junction. And another thing also we did in this work, we reduced the thickness of the recombination junctions as low as possible. The idea was making a kind of more resistive recombination junctions, and also exploring the influence of the thickness, because we never asked this question to ourselves, why we use a thick ISO layers, why we don't use a thinner one, because we want to minimize the TCO as much as possible due to the optical reasons. Then later on, we found actually in this work, 5 nanometer is working nicely and magically for our cells, but for the other the research groups, maybe the thickness range may vary between the 5 to 10 nanometers, but in our case, 5 nanometer was the ideal one. And we had a chance to enhance the electric field because of the enhanced the SEM coverage, and also a better homogeneity at the interfaces. So basically, this device end up with, adding all these improvements with 32.5% certified efficiency, and basically, and if this device also had a potential to reach the efficiency level around 34.7%. These are actually calculated values uh, from the PL and EL measurements. We constructed the JV curve, and this JV curve is showing the potential of the cell if the series resistance at the contacts can be eliminated. So transport losses are eliminated. Well, I mean, very recently, this is ongoing work, and actually, rather than the contacts, we also focus on the bulk of the perovskite. And so here, what we have done, instead of using the typical metal ammonium, formamidinium, cesium, SR cations, we start to use high pKa cation at the bulk. We use this cation as an additive. I'm not able to express the name at the moment because this is under submission. But basically, this enabled us the better passivation, defect passivation in the bulk, because of the nature of the molecule is a cyclic structure, and it has a 3 NH groups, and actually these NH groups are forming the hydrogen bonds with the iodide at the multiple directions, and it's actually well anchored to the cage, and it's quite favorable thing. And also it's helping for the enhanced stability. For instance, you see here the PL peak position from the perovskite layer after 30 minutes, keeping it at 1 sun and 85 C. So basically, it's also helping for the phase stability. So this device is actually last year in May, almost 1 year ago, it led actually another record efficiency with 33.7%. And actually with this device, for sure, again, we repeated the same measurement, and we found actually these devices have potential close to 36%. But in the long term, definitely, we predict these perovskite-silicon tandem cells can go above 37%. That is pretty much possible if we can really further minimize the losses. I will finish my talk, but actually just 1 minute maybe I'll take about talking about the stability, because last year, together with my colleague Tom Allen, we organized the panel discussion at Tandem P workshop, It was a quite fruitful discussion, and actually, and we had the panelists from academia and industry. But the main message of this panel was actually we need more efforts on for the stability aspects and the stability, durability, and reliability aspects. So basically, this is the thing. Actually, probably the community will be more occupied in the next period, and is also quite important because, and if you look at the situation back in 1980s when the silicon cells entered the market, basically there was no competition. The PV module prices were quite high, and there was almost no warranty actually. And but within the years, by building a trust on the products, recently many companies are offering the module warranties above 25 years. Some of them are above 30 years, and this trend will be increasing further. I mean, probably very soon the 30 years will be new standard. And for sure, in the beginning of my talk, I mentioned that the module costs are pretty low. So basically, the tandems also should be fitting in that range. And we cannot put tandems here again. It must be cost efficient. So there is a huge market barrier for perovskite-silicon tandems. We have to make it super efficient, super cheap, and super stable. So without working stability, it's difficult to realize perovskite-silicon tandems. Well, this slide is a bit busy. All right, yeah, thank you for listening. I'll be happy to get questions if there is nothing clear. Yeah, thank you.
Thanks a lot, Erkan. This was amazing. I learned a lot of things. There are several questions in the chat. Please start replying to that, and we will check them later. Now is time for Urs. We learn more about the fabrication of perovskite-silicon tandem solar cells. Urs is going to show you how to optimize these devices via simulation. Urs is a senior scientist here at Fluxim. He received his PhD from the ETH Zurich, and now he was working on quantum well solar cells. Since joining Fluxim in 2018, he's also a guest lecturer at the ETH, and here he's going to present an analysis and optimization of perovskite-silicon tandem solar cells by full optoelectronic simulation. Thanks, Urs. The floor is yours.
Thank you, Daniele, for the kind introduction. Yes, so my presentation is more about the modeling, what we can learn about these devices by using simulation. So one of the motivations for this kind of work is the obvious question that many researchers in PV have, namely how good is the solar cell that I fabricated? Of course, one way is just to look at the best cells. Oh, you have seen this chart in the talk before, but this is basically just a relative assessment. So you see, compared to others, how good it is. Usually, maybe not so good. But then the question is, how much better could it be than what it actually is? And this is the question also about the limits of the efficiency. So you have heard about that a bit in the previous talk. I'm going to go into a bit more details. We have also seen this graph here, which is basically the reference limit, the so-called single junction detailed balance limit, also called Shockley-Queisser limit, where the efficiency is just a function of one single material parameter, namely the energy band gap. So what are the assumptions behind this limit? Well, the first one is that you have a very idealized absorption. It's basically a unit step absorptance given by the band gap value. So this then provides basically the short circuit current upon integration of the solar spectrum with this unit step absorbance. Then the photons, they generate electron hole pairs with unit generation efficiency, and these electron hole pairs, they are thermalized with the lattice. So there's only one temperature, which is the one of the lattice. And this is also the ambient temperature. Then the transport is also idealized. So we assume that the carriers can be extracted with unit efficiency due to infinite mobility. And this also leads to flat quasi-Fermi levels or uniform splitting of the quasi-Fermi levels given by the external voltage. Then also the contacts are assumed to be perfect. So they're perfectly selective and there are no resistive losses. Recombination is limited to the radiative process, so the fundamental process. And this then gives you the second current that you need, namely the recombination current, now as a function of the black body flux. Here the chemical potential of the photons that are emitted is given by the external voltage. Then finally, the light that is emitted is assumed to be emitted into a hemisphere. So this gives rise to this Boltzmann loss that Erkan mentioned before. So these are some assumptions that lead to this efficiency, but then the question is, why is it so low? And this is also something that Erkan mentioned. There are some losses that are implied in these assumptions. And these are basically the transmission and thermalization losses of photons that are not absorbed, or high energy photons where part of this excess energy goes into heat. And this is exactly where the multi-junction or tandem concept starts trying to reduce these losses. But also here, the question is, what is then the limit in this tandem concept? Well, to get to this limit, basically we have to relax the unit step absorption. So we have now a slightly different absorption profile with two steps. Well, the bottom cell gets just the energy in this window up to the higher band gap, and then you have the unit step absorption of the top cell that has a higher band gap. Then also, if we look at two-terminal tandems, we have the condition of current matching. So the two currents need to be the same. Additionally, we assume that there is no voltage loss at the interconnect. So we have an ideal series connection and we don't lose any voltage. So the external voltage is the sum of the two subcell voltages. And then we can express again the two subcell currents in the same way as before, just now with the new absorption profile. If we do that for perovskite with a band gap of 1.65 electron volts and the standard silicon band gap, we find, well, that the tandem is quite severely bottom limited. So it's the silicon that limits the conserved current here. And also this configuration, well, it is not in the sweet spot of the detailed balance limit, but it gives around 40%. However, we have seen that currently the record efficiencies are rather in the range of 34%. So there is some discrepancy, and this, of course, comes from losses that are not accounted for by the detailed bands limit due to this idealization of the properties. So we need a more realistic assessment to get closer to what we actually have. So we need to increase the degree of non-ideality in our model. And the first step towards a more realistic assessment is to relax the unit step absorbance condition. So we now work with the actual spectral absorbance of our materials that we get from an optical model. And the main ingredient for this optical model for the absorbance is the layout of the stack. So you can see here quite a complex sequence of layers. And the second input or material parameter we need is the complex refractive index data. So you can see here the N and K values for the wide-band gap perovskite. So this is for a standard triple cation mixed halide perovskite from EPFL, and then the silicon refractive index data. So we now compute the short circuit current and the radiative dark current based on these the absorptions that we get from this data. So now the optical model, how it is chosen depends on whether you have thin film layers or incoherent thick bulk components. So for the thin films, and you have a lot of thin films in your stack, including the perovskite, the standard model is transfer matrix method, where you propagate the complex amplitudes of plane waves through a stack using the Fresnel coefficients at the interfaces between materials with different refractive indices. If you have, like we do in this case, also incoherent thick layers where the light loses coherence, so you have some part that is much larger than the wavelength of the light. What we use here is a kind of ray optics model that is based on the balance of the fluxes incident on different parts of the device. So if you have an interface, you have to make the balance of incident and outgoing fluxes. So now we have the combination of these two models for the propagation of incident light through our device to compute the absorptance in the active layers. And you see here that now this really deviates from the, well, unit step absorptance, even though it's actually quite close to 1 in a significant part of the spectrum that is absorbed. What you can also see is that the short circuit current that you compute based on that is not well matched. So even in this situation where you have a finite thickness of the top cell that allows some part of the light in the higher energy domain to be absorbed in the bottom, we have a bottom limitation. Now we can use this absorptance to compute actually the current voltage characteristics and then the power conversion efficiency at this optical limit, as I call it. This deviates from the Shockley-Queisser detailed bands limit due to the different absorptance. So first of all, the top cell short circuit current is reduced, but also the one from the silicon to the finite absorptance here. So you have a slightly lower PC, but also you have this problem with the bottom limitation. So you want to increase the photocurrent in the bottom cell. So this is the first thing you should do. And in order to see how one can do that, we need to look at the optical losses. So we compute the absorptance in the different parts of the device. And we see directly that parasitic absorption in non-active layers affect primarily the top cell absorptance and not the bottom cell. So it's not really useful to do a lot of work at this point to increase the current in the bottom. However, we have to not only look at the absorptance, but most importantly at the photocurrent that is produced. And we see also that this parasitic absorptance is in a region where there's actually not too much photon flux. So another representation is then more useful that directly translates into the spectral current density. And so we can actually quantify the different currents, the one that is absorbed in the active layers and then the parasitic losses due to absorption in the non-active layers, and also the significant reflection loss that we still have here in the region of the bottom cell. So what we can see is that there is a domain where there is an overlap in absorptance, and this can be used to redistribute the absorption from the top to the bottom cell to mitigate this mismatch in the current. And of course, what you have to do is to reduce the perovskite thickness, which increases the silicon photocurrent until you reach a current matching condition. So you can see how here in this overlap region, the contribution of the bottom cell increases while the top cell contribution decreases. If we do that, we find a matched situation. However, the current is still quite low, so we increased the efficiency a little, but it's still not ideal. So therefore, we now look at this part where we have significant loss due to reflection. And we have seen in the previous talk also that one way of reducing these losses is to increase the light path length in the silicon via scattering at the texture. So first, we consider a situation where we have just one interface that is textured, which is the rear interface here. So the incident light scatters into larger angle and the light path in the silicon then is increased. We model this in our software, which is called ZFOS, using validated multi-scale approach. So first, you compute the properties of the thin film part, the coherent stack, as we call it. In this case, it's the coherent stack here on the rear side, on top of this texture. And this then is used in a ray tracer to compute the scattering properties of the complex interface. And this again is used in the transfer matrix type retardation model as before. So you have then just the propagation again in the entire stack, but including the scattering at the interface. If we do that, including this scattering texture, we see that indeed we can gain a lot of additional current here in the long wavelength region. There's also a small decrease, but this is again the situation where we find the optimum thickness for current matching. So now we are actually quite close to the Shockley-Queitzer limit. That, well, how it is on this idealized absorption. But this is not the end of the story, because you could also have a double-side texture. And in this case, we assume not a planarized perovskite, but this conformal coating that I can also mention. This gives you an additional current, not only in the bottom cell, but also in the top cell. So again, this is the situation that is already optimized with regards to current matching. And since we have now larger absorption in the silicon, also the optimum thickness of the top cell of the perovskite shifts to a larger value. So we had for the flat case, we had 380 nanometers. For the fully textured, we have 530 nanometers. Again, we can have a look now at the situation regarding the losses, and we see that indeed the reflection loss is strongly reduced. But as Erkan also mentioned, there is now room for improvement regarding the parasitic absorption, especially at the rear side, for instance, in the silver. Now we find that we actually exceed now the detailed balance limit. So maybe this is not such a good limit after all, because the assumption of this unrealistic absorption seems to be non-ideal for the tandem configuration. And this is actually the maximum efficiency that you can achieve with this NK data if you only change the perovskite thickness. So this was the optical situation, and we have now these optical limits. But if you compare it with the measured performance for this rear textured cell, there is, of course, still a big gap. So the question is, how can we get from this optical limit to the measured performance? And of course, the answer is that we need to relax not only the optical idealizations or assumptions of the detailed balance limit, but also the electrical assumptions. So there will be transport non-idealities like low carrier mobilities or potential barriers, or even some fields that prevent efficient carrier extraction. Then also there are non-radiative recombination losses in the bulk and the interfaces. There's also Auger recombination, and then contacts can be non-ideal regarding the alignment of the energy levels or the selectivity. There might be some leakage even. And to accommodate such non-idealities, we have to combine the optical simulation with an electrical model. The standard electrical model for solar cells is based on the charge continuity equations, including a generation and recombination term, with currents that are described by drift diffusion terms for electrons and holes, and this is coupled to the Poisson equation for the electrostatic potential. Now, in the case of perovskite, we also need to include mobile ions in the drift diffusion Poisson framework. And in perovskite, we also have the situation that we have a highly emissive system, or let's say we are often relatively close to the radiative limit. And in this situation, reabsorption effect and photon recycling can also start to play a role. Now, for two-terminal tandems, as we are considering here, we of course also need a model for the series interconnection of the subcells, meaning the recombination junction. So this is how we implement the full tandem structure electrically. So there is a range of additional material parameters that need to be included now, in addition to just NK data and the layer thicknesses. Most importantly, the energy levels of the material, so the band edge energies for conduction and valence bands, or homolumo, depending on whether you talk about inorganic or organic materials. But of course, there are also more parameters like mobilities, lifetimes, and so on. Now we have here the perovskite tops and a silicon heterojunct bottom cell integrated in the full tandem, and they are connected here via the recombination junction. And this is the place where you have the recombination of electrons and holes from the subcells that enable the flow of charge across the entire cell. So how does this look like? For instance, at short circuit conditions, you can see here the component currents of electrons and holes that increase within the absorbing region. So you have the effect of generation here. And then you have the recombination of the generated carriers at the recombination junction. And overall, the total current is conserved over the entire device. Now we start with looking at the situation of the single junction configuration subcells and the filtered subcells in the tandem configuration. This allows you to assess the losses that come from the optical situation. So we have a slightly reduced conserved current here, which is still limited by the bottom cell. So the optics did not change, of course, and we can now compare also the electrical situation in, let's say, isolated condition compared with what happens inside the tandem. And then we can compare these subcell characteristics with the full tandem characteristic. For instance, by just adding the subcell or the filtered subcell JV curves. In this case, we see that it's a perfect match. So there are actually no losses that incur from connecting the device into series. So it's quite an ideal situation. Well, this is at the Auger limit. So this is as good as it gets, including transport. What does it mean? Well, as I said, the optics is already the one that we looked at before. So we have about the same current, but the electrical situation is still idealized. So we have a higher VOC, a higher fill factor, and overall a larger efficiency. Now, having the full simulation electrically allows us to inspect the situation regarding the transport properties at the operating point of the device. So, for instance, the maximum power point, we can inspect the quasi-Fermi level splitting, potential gradients we find in the quasi-Fermi levels, or also the alignment at the recombination junction to see whether there is an issue with voltage losses due to non-idealities already at this level. Now, of course, we want also to inspect the impact of defects. This is actually for a different device, so it's a slightly different current. And here I increase the density of defects in interface regions of the perovskite top cell, which of course then leads to a drop in the open circuit voltage and also fill factor. What is interesting is that you can actually propagate now this loss from the single junction perovskite situation to what you have in the tandem, and you see that actually the impact on the tandem level is more dramatic. Also, you can see that the situation changes regarding the optimal thickness when you include defects in the picture. So a more defective device here requires a larger perovskite layer thickness for an optimum performance. Now you can combine all these different levels of idealization into the full loss analysis. So this is quite a crude picture on this at this point. So starting from the optical limit, you go where you have idealized transport, but realistic optics, to a limit where you have realistic transport, but only, well, Auger recombination, let's say, and radiative in the perovskite, to the situation where you have also the non-radiative recombination losses, defects at interfaces, and so on. Now you can refine this picture according to your needs, because you can just switch on and off different loss channels in your transport model. So you can split this into different contributions to different interfaces, different material contributions to bulk recombination, and so on. Also, you can have a look at the impact of photon recycling, luminescent coupling, which is actually something that Monsieur and Simon Zeder presented already. So what do I mean by photon recycling and luminescent coupling? Well, basically, photon recycling is the reabsorption of light emitted within the same layer, while luminescent coupling is reabsorption of light emitted by the perovskite in the silicon bottom cell. So it's additional current that comes actually from the perovskite emission. Well, we developed a formalism that allows us to actually compute with spectral and spatial resolution where we have this additional generation in our device, both for photon recycling and luminescent coupling, and we can couple this to the full transport picture. This allows us to quantify the impacts of photon recycling, luminescent coupling, not only at the radiative limit, but also in the presence of recombination at defects, so including, for instance, Shockley-Reed Hall. And we can not only have a look at photocurrents, but also at the actual efficiency gain that you can have from photon recycling and luminescent coupling. So finally, this simulation approach is not confined to steady state properties, but we can also inspect transients. So then you solve the drift diffusion equations in time domain or with time dependence. And this is something that can be used to have a look at things like hysteresis. Now, here, this is actually by my colleague Davide Moya. He looked at different situations for this perovskite-silicon tandem. First, the situation where the silicon cell is limiting. And in this situation, one finds that the potential across the perovskite cell is approximately constant for all the different points of operation. This also means if you compute the the transient voltage scan, there is negligible hysteresis. On the other hand, if the perovskite cell is limiting, if you change the point of operation, there is actually also a change of the voltage across the perovskite. So it changes with the applied voltage, and this leads to quite pronounced hysteresis. So the bottom line is that the limiting subcell determines the hysteresis behavior that you observe. Okay, so in conclusion, I try to show that if you want to do a device-specific performance assessment and also optimization, you need to consider the optics of the device. So you should use something like an optical limit rather than the standard detail balance limit. We performed the optical loss analysis in optimization on flat and textured perovskite-silicon tandems based on this multi-scale optical model. And I also showed how optoelectronic device simulation, if you explicitly consider the recombination junction, enables the assessment of electrical losses, not only at VOC or short circuit, but at the actual point of operation of your device. So with that, I would like to thank my colleagues in the R&D team and also in the ZFOS software development team for providing me with this nice tool, and also the colleagues from PV Lab in Neuchâtel that provided the NK data and some experimental results, and also the Swiss National Science Foundation for funding in the framework of the Radicals project. Thank you very much.
Thanks a lot, Urs. It was a great understanding of how perovskite-silicon tandem solar cells work. There are a lot of questions, but we are running late in time. Let me check quickly. Urs, can you use ZFOS to simulate also for the terminal tandem solar cells?
Yes, well, 4 terminal tandems are not that let's say involved what regards the requirements on the electrical simulation, because you don't have this recombination junction in between. The optics basically is the same, but then you just do the individual simulations under the condition of voltage matching. But the individual simulation of the subcells you can do separately. Yes. Using ZFOS is no problem.
And one question for you, Erkan. Is there a particular reason for using 2 perovskite over Ne for perovskite in your solar cells?
No, well, I mean, basically, 2PEX is working nicely because it's the perovskite formation on 2PEX is usually much better. But actually, we also use Me4Pexy. But in this case, we have to do treatment under the surface. Actually, this is well explained by also the HZB team, and they showed the wettability problems on Me4Pexy, and this problem is still valid on the textured interfaces. But that specific work in the work that published in Nature, we use 2Pexy, but in the recent works, we also start to explore Me4Pexy. And it's correct. I mean, Me4Pexy is giving a bit better voltage, around, I have to say, maybe 10 to 20 millivolt higher voltage. But actually, time by time, it comes with the cost of lower fill factor of the devices because of the coverage problems, and it must be well engineered.
Right. Thanks a lot. There are a lot of questions. We have no time left. Both presentations are going to be on YouTube in a couple of days. We will see you in 1 month with a new webinar. And thanks a lot for watching this one. And thanks, Erkan, again. Thanks, Urs. And see you soon.
Yeah, thanks
Bye.
for the invitation. Yeah.